If you would recall, we've looked at addition, where we only add things that are the same, and when we add them, it doesn't change what they are. That was Leach's rules for addition. We've talked about multiplication. We've talked about multiplication as being repeated addition, and also multiplication is a way to get sameness. We can use multiplication to get a common currency or a common denominator so that we could then add, because we only add things that are the same, and when we add them, it doesn't change what they are. So we talked about the rules for addition, the rules for multiplication, and now we're starting to put those things together. So what if multiplication and addition show up in the same problem? Here are the rules for multiplication and addition together. This is the big one. Multiplication goes before addition. So this means if I have 5 plus 3 times 2, I have two operations, plus and multiplication, addition and multiplication. The multiplication goes first. I'm not actually looking at 5 plus 3 because the 3 is being multiplied by the 2. So 5 plus 3 times 2, we do the multiplication. 3 times 2 is 6. Then we get to do the addition. 5 plus 6 is 11. If we're like, oh, wait, that's not what we wanted. I wanted the 5 and the 3 to go first because they both have a 2. If we want the addition to go first, then we have to use parentheses to say, hang on, do this addition first because this is going out of order. So 5 plus 3 is in parentheses, so that's 8. Then we do the 8 times 2 is 16. Now instead of just the 3 gets the 2, the 5 does not get the 2. The 3 and the 5 both get the 2. Any questions? This actually is related to things that we're going to see later on. If we know that if we're going to add polynomials, that's an algebraic object, so we got to think adding polynomials. Sameness in polynomials is like terms, the same variables with the same exponents. And so if I have an expression that says something like 5 plus 3 times x, I know I'm not going to add these things. First of all, we only add things that are the same. This is a constant term. This is an x term. They're not the same. Also, this multiplication has to go first because multiplication goes before addition. So I can't add the 5 and the 3 because the 3 is getting multiplied by this x. This x is saying, hold on, I got to multiply by that 3 before the 5 comes along and we add. So it works in a bunch of different ways. We're not adding things because they're not the same. Also, I've got to take care of this multiplication before I do any addition here. However, if we're looking at the expression 5 plus 3 times x, the parentheses say, go ahead and do this addition first. And then we see that we can add those things. And so this is going to be 8x. Any questions? All right. So the other thing, the other bullet point under multiplication and addition together is that multiplication distributes over addition. We usually remember this as the distributive property, but I don't like thinking of it as the distributive property because there's going to be another one coming up. So multiplication distributes over addition. This is how we can remove parentheses from an expression when it involves multiplication. The reason that we can distribute is that this operation in here is multiplication. But then this is just the familiar distributive property. If I have 5 and 3 in parentheses, I can use the distributive property to remove the parentheses. So we think about it by saying we use the distributive property to remove parentheses. I'm not just going to end the sentence here. We use the distributive property to remove parentheses from multiplication. That's the important part. We're doing a multiplication, and that's why we get to use the distributive property. So if we think about the distributive property, if we look at this expression, and instead of a 2, we have x, we have 5 plus 3 times x, like we had before, where this is multiplication. I can use the distributive property and say that this is 5x and 3x. Now they are like terms, and that's still 8x. Also note that if I take the x out and put in a 2, I get 16. 16 times 8, sorry, 8 times 2 is 16. 5 times 2 is 10, 3 times 2 is 6, 10 and 6 is still 16. So everything's nice and consistent. We like it that way. We get to use the distributive property because we're moving parentheses from multiplication. Any questions? All right. So let's talk about some things. I actually know that all of you knew this distributive property already. I like to point it out because there are certain things about the distributive property that I want to say, but we use the distributive property in arithmetic as well. Note, we use the distributive property in arithmetic. We usually don't call it the distributive property when we teach it to you because that maybe sounds too fancy for your age, maybe when you were learning this. I'm not sure. I don't teach children. I don't really understand how to talk to children correctly. So I just think of them as miniature adults. It's very Victorian of me. So don't let me raise your kids, is what I'm saying. We use the distributive property in arithmetic for multiplication. I need to make sure that we say that. For multiplication. For multiplication. This A times B plus C is AV plus AC thing is a multiplication thing, not a distributive thing. It's a multiplication thing. It's how the distributive property applies to multiplication over addition. But we already know how to do this. We already do this. If we imagine I wanted to take, say, I need numbers, 23 times 7. If we think about multiplying 23 times 7, the way we would set this up in the standard algorithm is to set up the 23 times the 7, and then multiply the 7 by the 3, and then the 7 by the 2. What the algorithm sets us up to do is to multiply the 7 by each of the digits of the 23. This setup helps us remember to multiply the 7 by each of the digits of the 23. This setup helps us remember to multiply the 7 by each of the digits of the 23. So we would say 7 times 3 is 21. And then we would say 7 times 20. I know some of you would put a 1 down here and carry the 2. That's okay if you do that. You're doing the same thing. But I want to do the 7 times 3 is 21. Then I'll do 7 times the 2, but that's not a 2, that's a 20. 7 times 20 is 140. Because 7 times 2 is 14, then drop a 0 on it. And then when we add them up, we get our total of 160 something. We're just using the distributive property because we're looking at the 23 in parts. We're observing that 23 is actually 20 plus 3. And then we're just using the distributive property. Setting things up this way is just helping us remember to use the distributive property. So we have the 7 times the 20 is 140, plus the 7 times the 3, which is 21. And so we get a total of 161. We read the 23 as a 20 and a 3 because that gives us the most zeros. And so that's just the standard way of doing things. That's not the only way that we need. That's not the only way we can get about this. But this is us using the distributive property in an arithmetic environment. Any questions? So we should recognize that we can totally be sneaky about this. We normally think of 23 as 20 and 3. In German, we would actually say 3 und 20, 3 and 20. That's why that song is like 4 and 20 blackbirds baked in a pie. That's just saying, instead of saying 24 blackbirds. Because you need more syllables to make the rhyme go. But 23 is not just a 20 and a positive 3. We can also think of 23 as 30 negative 7. 30 times 7 is 210. 7 times 7 is 49. And 210 minus 49 is still 161. So another way to say 23 is 30 negative 7. More ways to go about a problem is better than fewer ways to go about a problem. Any questions? All right. So this is when we do multiplication. When we multiply numbers, multi-digit numbers like this, and we don't just use a calculator, we are using the distributive property. If we write down this algorithm, however we implement the algorithm, it's still just a way to get multiply each digit of the 23 by the 7. 7 times the 3, 7 times the 2. Any questions? This helps us understand how to expand the distributive property. So this multiplication algorithm is just the distributive property, and an application of the distributive property. That means if I have multiple digits in the 7, instead of 7, I have a 17. That's the one that we did before. It's still just a distributive property. So this page 2, this page 2. So even if we have more digits in the 17, it's still just a distributive property. So for example, sorry, the 7, 23 times 17. This is still just a distributive property. In this case, the distributive property is going to ask us to multiply each digit of one number by every digit of the other number. So I want to distribute the 7 to the 3 and the 20. Then I'm going to distribute the 10 to the 3 and the 20. So the algorithm is going to ask us to multiply each digit of one number by every digit of the other number. Distribute each digit of one of the numbers over the other digits. Multiply each digit of one number by every digit of the other number. That is, distribute each digit. Oops, I spelled digit wrong. So I need the 7 times the 3. 7 times 3 is 21. I need to multiply the 7 times the 2, or sorry, 7 times the 20. 7 times 20 is 140. Now I've distributed the 7 to the 3 and the 20. Now I need to distribute the 10 to the 3 and the 20. So next up, I take the 10 times the 3, and that's 30. And finally, I take the 10 times the 20, and that's 200. Now we just turn it into an addition problem. So I got 391. So 391. This is the same structure as FOIL. This is the same as FOIL. For those of you who remember FOIL. This is just FOIL, but applied to numbers. And using the normal way we think about numbers as additive. So we think of this as a 23 and a 17. And we just make all the pairs. 7 times 3, 7 times 20, 3 times 10, and 20 times 10. Same for products that we're adding together. FOIL just does it in a different order because it's FOIL 200. Outer is the 20 and the 7, 140. Inner is the 3 times 10, 30. And last, 3 times 7, 21. Then we just add them all up. Same process. FOIL is just this algorithm that we normally apply to polynomials, or it's just how we adapt the algorithm that we already know to polynomials. Any questions? All right. If we allow ourselves to be clever about how we read numbers, we don't have to think of 20 as 20 plus 3. We could do like we did in the last problem. Maybe 23 is 30 negative 7. That's not a real number. That's a Calvin and Hobbes number, if you're familiar with Calvin and Hobbes. But we might read 23. This is a weird side note, and I recommend not doing this as a common practice, but 23 we could think of as being 30 negative 7, and we can even mess with the 17. Maybe 17 is 20 negative 3. 30 minus 7 is 23. 20 minus 3 is 17. This is still 23 times 17. Let's find out what happens. First, 30 times 20 is 600. Outer, 30 times negative 3 is negative 90. Inner, negative 7 times 20 is minus 140. And then last, negative 7 times negative 3 is positive 21. And when we add all these numbers up, let's see, 621 minus 90 minus 140 is still 391. Just like it was up here. just like it was down here. We're just representing the numbers in a very strange way. 30, -7 instead of 20 and +3. Any questions? All right. One other tip that I want to get recorded is how we can add and subtract things. So my recommendation is that you subtract things in pieces. So some of you I saw on your addition problems, some of you I saw were doing this already. Some of you were doing this already, subtracting by place value. So that's good. So let's first take the 600 and the 21. I'm going to add those together. That's easy, 621. I picked those because I got 2 zeros here to stick the 21. But now I need to subtract 90 and I need to subtract 140. And I'm going to subtract in place values. So I want my strategy to be subtract by place value. So here's our strategy, subtract by place value. The reason that this came up is subtracting by place value is using the distributive property. So let's just take this part, the 621 minus 140. So if I take 621 and subtract 140, I'm thinking of it as 621. I spelled 2 wrong. There we go, saved it. I need to subtract 100, and I also need to subtract 40. That is, I need to take 621 and subtract 140. Oops, scroll. If I just think of these two terms, these two numbers, 621 minus 140, we can use the distributive property and subtract by place value. Now, this is not what we would write. It'd be crazy to write this much. This is what we want to think. So this is not what we're writing. This is what we are thinking. So this is what we are thinking. It's not what we're writing, it's what we're thinking. So 600, in our minds, we're going to say 600 minus 100. 621 minus 100 is 521. 521 minus 40 is going to be 481. Because I take off 2 and then I take off 2 more. 2 down to 50, 2 more down to 48. Then if I just do 481 minus 90, we end up with 391. Once again, all this stuff is going to be taking place in our heads. It's not what we write down, it's what we think. Any questions? The point of being in a math class is to avoid having to write this whole algorithm out and do all these steps. And just look at the 23 times 17 and break it apart into pieces that we can easily parse and come up with the 391. Then, being in an algebra class is about taking this algorithm and applying it to other things. Any questions? Comments? Snide remarks? All right, so I'm going to reiterate. I think I said this last time. It's not about doing this quickly. So if you take an algorithm that you learned when you were a child and compare it by speed to doing things in this new way, the new way is always going to lose because you've been doing the other thing since you were a child. You've got a lot more practice with that than you do with this different way of thinking about it. This different way of thinking about it is going to take work because you have habits that have been built up for a long time. And I'm not asking you to break those habits. I'm asking you to expand on those habits so that we can further expand on your knowledge base of algebra without having it be 1,000 new things, but rather say a couple of variations on 1,000 variations on one thing. Any questions? Comments? Deep thoughts? All right. I've got one more thing to drop on you today. We're going to let this multiplication and addition thing just kind of sit while we look at the next operation before we start looking at inverses. I just want this idea out there. So let's see, page 2. Exponents. This is our new operation. This is the operation for the day. This math class is brought to you by the operation exponents. So I want to talk about how we think about exponents in the same way that I talked about addition and multiplication and how we think about them almost automatically. We need to break down the things that we do automatically to see why we do those things and why they become so efficient for us. So let's just talk about how we think about exponents. Here are the two things that I want you to think about exponents. Exponents are, does anybody know what I'm going to write here? Let's just do a quick test. Think about the things that I said about addition, the things that I said about multiplication, and the things that I said about multiplication and addition together. And I'm going to say two things about exponents, and the first one is exactly that. I want to state explicitly what we mean when we write an exponent. An exponent is repeated multiplication. I like it when I am so predictable. So that's good. Nicely done. Exponents are repeated multiplication. So if I have, let's say, for example, a bunch of things that are the same. Remember, it's just like repeated addition. The things all have to be the same. If I have three things that are all the same, say 2 times 2 times 2, I can say this, I'm multiplying all the same thing. I don't want to have to write these things all the time. I want to somehow say I'm multiplying 3 2's. I can't put the 3 in front of the 2 because that means multiplication. That means 3 2's added together. So I put the 3 on the other side of the 2, but then it'll look like 23. So I make a superscript. We've really only got a couple of places where we can put the things together. So an exponent is written on the, let's see, that's the right side of the number as a superscript. So exponents, superscript. On the right. In this case, we refer to 2 as the base of the exponent. 2 is the base of the exponent. 2 is the base. B-A-S-E, not B-A-S-S. So 2 is the base of the exponent. So 2 is the lower one. The exponent sits up top. I guess in this case, it is kind of the BASS because we have to drop the base because it's lower. That was terrible. I'm way too old to say that, so I apologize. The way we read this expression is to say 2 to the third. So we pronounce this by saying say 2 to the third. We say the base as a number, then we say the words to the, and then we say the exponent as an ordinal. So like first, second, third, fourth, fifth, and so on. So the way we pronounce that is to say 2 to the third. There is another way to write this which we need to be familiar with in a single line syntax world of text messaging. Hang on. There we go. So if we're going to use our phones to do this, I just did that specifically so I could show you a picture of my dog, because my dog is the cutest. That's Colson. So the other way to write this, let's suppose that we're texting our friends back and forth and we need to say 2 to the third, and we don't want to type this whole thing out. There is a way to do that. So we have single line syntax for this. I refer to it as single line syntax. I say 2, and then we make this little arrow pointing up. And then everything's on one line. This is what I call single line syntax. Syntax is just a word meaning how we write things or type things. And single line means if we don't have the ability to write exponents, we put this little arrow pointing up and say, and we pronounce that arrow as to the. So exponents are repeated multiplication, 2 to the third. That's number one thing to say about exponents. Exponents are repeated multiplication. Number two thing to say about exponents is about exponents and the way they distribute. So exponents, once I write this down, this will unlock the secrets of algebra. This is one simple trick to crush your next algebra exam. Exponents distribute Now remember, once I write this down, algebra will be simple forever, and everything will be perfect. This will make everything snap into place. So exponents distribute. Now remember, this is going to fix everything. So once I write this down, only if I write it down right now though, will it work. So exponents distribute. Oh dang, look at the time. All right, that's going to do it for today. What you need to do before tomorrow, or actually before Friday, is to find out what exponents distribute over. Tomorrow we're going to talk in the 820 section, we're going to talk more about converting from one unit to another using multiplication. We're going to make a nice solid process for that, so we can do that in many environments. And then on Friday, I'll finish this sentence. Man, if only I could have got to it today, that would have solved all of our problems and everything would have been perfect. It would have been like magic, but unfortunately, I'm just kidding. I want you to look up what exponents distribute over because it's pretty cool. All right, that's going to do it for today. I'll see y'all on tomorrow or Friday, and thanks for playing.